Is it working?
It looks good.
Great.
So it's my pleasure to introduce John Kopper of Penn State University, who's going to talk about the cohomology of general tensor products of stable sheaves on the projective plane.
All right, thank you. Thank you for the introduction and the chance to speak. And thank you all for coming to my talk, or not leaving after Sasha's talk, maybe. Everything I say today is joint work with Izzet and Jack. So you can I'll say it now and never again. And the plan today is to do exactly what the title of the talk says, which is to compute the cohomology of general tensor products of stable sheaves. And maybe let me say a couple things before I get into the details. The first is that we've done a lot of this type of thing this week. We've seen a lot of these definitions, so I might be a little cavalier and not define things. So if you feel like I need to define something for you, please ask me to do so. The second is that I don't know that I want to spend a huge amount of time motivating the question of what are the cohomology groups for tensor products. I'll say maybe a little bit in a second, but I think I'm at a Moduli conference and I believe myself to be among friends. And so I won't spend a whole lot of time trying to convince you that this question is interesting. So anyway, that's the plan. The goal is to do, as I said, to compute the cohomology groups of a tensor product of two vector bundles that are stable and general in their respective moduli spaces on P2. And I want to tell you what all those cohomology groups are, and I will essentially give you a complete answer to this question, modulo some things. Okay, and the main convention I'm going to have is if I take a Chern character, I'm going to think of it as the rank, the Ch1 and the Ch2, and then my usual other invariants will be the slope, which is Ch1 divided by the rank, and the discriminant, which I'll denote delta, and that's going to be 1/2 of the slope squared minus Ch2 over R, which is maybe a slightly different normalization convention than you may be familiar with, but it's not. It's like 2R squared times this is maybe the other one that people use. Okay. Here's one motivation that I want you to think about. It's probably the only one I'll say, but we can use this type of theorem to construct effective divisors on the moduli space. So for example, say I'm in the situation where I have two characters, and when I take their tensor product, the Euler characteristic is 0. What we might expect in this case is that there are no non-zero cohomology groups. Let me do capital letters for bundles. That all of these groups vanish for V and W general. And then the locus where this fails, the locus where there are cohomology groups, is going to form some kind of theta divisor. So some theta divisor in each moduli space, M of V and M of W. This type of thing can be interesting if I want to, say, compute the effective cone, which has been done. But it also, if I know that I have this situation, then these moduli spaces are candidates for strange duality, which is still very much an open question for P2. And so this type of construction of divisors gives you a lot of rich birational geometry. And it's something that I hope people will think about during and after my talk. Okay, that's it for motivation. Let me tell you what you should expect the answer to be. And the theorem is going to be that the expected answer is often the correct answer. So I'll call this the expected cohomology, or the non-special cohomology, which is maybe a term that I have to justify. You also see in the literature the natural cohomology. This is like a word I see people using in like the 80s for curves. So I'll say V has expected cohomology. If it has at most one non-zero cohomology group. And if it doesn't have that property, if it has, you know, more than one non-zero cohomology group, I'll say it has unexpected cohomology, or maybe special cohomology, or maybe unnatural cohomology, which I kind of like the sound of that. And the point of this expectation, at least, is that this means I can compute the cohomology very easily. This means I can compute all of these groups using the Euler characteristic and the slope. How does it work? You know, if the Euler characteristic of V is less than 0, then I can't have H1, or sorry, I can't have H naught or H2. I must have H1, right? If the Euler characteristic is negative, I have to have at least some H1, and if that's my only non-zero cohomology group, then the other ones vanish. And then if chi of V is greater than or equal to 0, then this means that I have either H naught or H2, so I get H1 equals 0, and the other group I have is determined by the slope. So I'm on P2, so I can say this. H2, let's say H naught equals 0 if mu is less than 0, and H2 equals 0 otherwise. So just using slopes and Euler characteristics, and the fact that I'm talking about a stable sheaf, I can read off the cohomology here. So that's what we kind of expect or perhaps hope for. But it will turn out that that's not always the case for tensor products. It is, however, the case for just general bundles. So let me state the theorem of Göttsche and Hirschowitz the following way. If little v is the Chern character of a stable sheaf, that says stable. My B is not very good. Sheaf, then for V and M of V general, V has expected cohomology. So this kind of justifies me also calling this non-special cohomology. The cohomology of the general element of the moduli space is this expected thing, where at most one cohomology group is non-zero. This is, of course, not necessarily going to be true for general tensor products, but we can hope that it is. The next theorem I want to tell you about is a theorem about tensor products. It's due to Drézet in the 80s. And Drézet tells us that the tensor products of two vector bundles have expected cohomology if those vector bundles are exceptional vector bundles. So V and W are exceptional. And of course, I'm always working on P2 here. Then V tensor W has expected cohomology. And here, of course, it doesn't make sense to talk about a general element of their moduli spaces, because when I have exceptional bundles, the moduli space is just a single point. And so this is just true for exceptional bundles in the greatest generality you could hope for. Okay, and so these two theorems at least tell us that we can hope that tensor products of general bundles have the expected cohomology, but they don't tell us that they do. The next theorem in this direction is one from a paper I'll mention a couple of times today, where so my two co-authors, Izzet and Jack, as well as Matthew Wolf, actually constructed some vector bundles that had the expected cohomology in the case that the Euler characteristic of the tensor product is 0. So for any V, so there's a little v, the Chern character of a stable sheaf, there are Chern characters that are associated to V in some way. I'll say U plus and U minus, such that chi of V tensor U plus and U minus is 0, and V tensor U plus or U minus has expected cohomology for the general elements in those moduli spaces. So, I mean, they proved a good deal more than this, but the point of this was somehow they were trying to construct effective divisors to describe the edge of the effective cone, and they had to come up with some actual Chern characters that satisfied this property in order to do that. And so that's something they've done. And then the next thing I want to tell you in this direction is the first new result that I'm telling you about today, which is not our main theorem, but it's a corollary of our main theorem. And it's the easiest thing to state. So I'm going to say it now. And if you remember nothing else from my talk, you can remember this. So we're gonna start with two Chern characters, V and W of stable sheaves. I'm gonna suppose W, the Chern character, is sufficiently divisible. And I'm also going to assume that the discriminants of my V and W are at least 3. That's a W. Then we have expected cohomology. So this discriminant number is the number I defined at the start of the talk. And the way I want you to think about this, first, I don't want you to spend a lot of energy worrying about the sufficiently divisible hypothesis on the character of W. That's a technical hypothesis that we seem to need for our proof, but it's not clear that the theorem fails without it. What I want you to imagine here is that essentially for large discriminants, we have expected cohomology of tensor products. The only way that this can fail to happen is in very specific situations. The full theorem I'll state in a minute describes those situations, but it just doesn't happen that often. So that's the main takeaway I want you to have. Now I've drawn a horizontal line at the bottom of the page, which means I should pause and ask if there are any questions.
So I didn't understand the U plus minus in the previous theorem. Is that?
Yeah, so these are just specific Chern characters. It's like examples of Chern characters for which we have the expected cohomology.
Are they independent or something?
They describe like the 2 different edges of the effective cone somehow. Yeah.
Got it.
So if we get there later in the talk, they'll show up again, and the fact that there's 2 of them and that they are independent will be significant. Thank you. Any other questions? Okay. So to state the theorem, I need to develop a little bit of terminology and notation. And the reason is essentially because it's not true that we will always have expected cohomology. But what is true is that the cohomology groups can be determined from Euler characteristics and slopes, sort of like it could be in the expected case. But it's not necessarily just the Euler characteristics of V and W. I'm going to attach a little bit more data to them, or maybe put differently, I'm going to break up the vector bundle V into a couple extra pieces, and we'll analyze those separately. And so the concept I need is that of the corresponding exceptional bundle. So let me define that. And I guess I should, just to be pedantic, I should say that this is the primary corresponding exceptional bundle that I'm going to talk about. And that'll be because later on I'm just going to assume my slopes are all positive, because I can do that by Serre duality. That's coming up. Okay, so what is the primary corresponding exceptional bundle? So I start with my Chern character, say V. So then E plus, which is the primary corresponding exceptional bundle, is the exceptional bundle with the following property. Such that for any other exceptional bundle, so for any, let's say G exceptional, with slope bigger than mu of E plus, we have the following Euler characteristic. We have chi of G tensor V is greater than 0. So E plus is the exceptional bundle with this property of smallest slope. So among all the exceptional bundles that have the property that when I take something of higher slope, I get positive Euler characteristic, E plus is the one with the smallest such slope. So it's the smallest slope exceptional bundle like this. So the definition is a little confusing, but it's also probably not clear that it even exists. It does exist. And I don't know an easy way to prove this, but I know that it shows up, the proof shows up in that paper that I mentioned by Izzet, Jack, and Matthew Wolf. So it's the same paper I've already cited. Okay, so this is some exceptional bundle that I've chosen to associate to my vector bundle. Okay, that's one piece of the puzzle. I need to describe one other piece of the puzzle that I'm associating to V. And for simplicity's sake, I'm going to make the assumption, I'm going to assume that the Euler characteristic of V tensor, its exceptional, its primary corresponding exceptional, is positive. So if you read this definition very carefully, it does not require that the exceptional has positive Euler characteristic. It can actually be 0 or negative. And those break up into different cases. And I don't want to spend all day describing the differences between those cases. They're not super important for our purposes today. So I'm just going to make this assumption for the rest of the talk. Well, for the rest of this section of what I'm talking about. Okay, so that's one piece of the puzzle is the primary corresponding thing. And then the other piece of the puzzle is this complex that I'm going to associate. So how do I do it? I take the canonical evaluation map that looks like this. I take the dual of my primary corresponding times Hom E plus dual V. This thing naturally maps to V, right? So this is some canonical evaluation map. And what I want to do is take its mapping cone, which I guess I've forced myself to rewrite the same thing. Okay, so this maps to V. And then this thing has some mapping cone, which I'm going to call K. And K is a complex. It may not be a sheaf, but it is a complex. And so at least there's that. But I can describe it a little more explicitly. What does this complex look like? So I'll remind the experts and maybe inform some people for the first time. We have a spectral sequence due to balancing. And I'm going to take a balancing spectral sequence somehow corresponding to the exceptional collection or an exceptional collection involving this primary corresponding exceptional bundle. So it's a balancing spectral sequence somehow constructed from an exceptional collection. I'll write it F, G. So each of these is an exceptional bundle. And then our friend E plus, and I'll take the dual. So this guy here is the primary corresponding that I defined above. And the E1 page of the balancing spectral sequence looks like as follows. I have F with some power. I have G with some power. And then there's a 0. And then here I've got zeros. And then E plus dual, again to some power. And this thing converges to my bundle V in degree 0. So the fact that it converges to V is A, not obvious, and B, is only going to be true if you have the right numbers, M1, M2, and M3 here. But the point is that this spectral sequence converges to V in degree 0. At least for the general V. And what does this have to do with my complex K? So here's somehow, this is my primary corresponding exceptional, maybe with a dual. And then this here is supposed to be my K. So K is the complex that looks like this. M2, I guess. And so it really shows up very explicitly if I know about the valence and spectral sequence. The fact that this is the same as what I've written above is, again, maybe not quite obvious, but it's not so bad. So these are the two pieces, the primary corresponding exceptional and this complex K that I've just defined for you. Those are the two pieces of information I need to state the theorem. So are there any questions before I go on? These are the two important definitions. Okay. Let me say just a couple things about K. The complex K is this sort of the same thing as a stable representation of a Kronecker quiver. So the Kronecker quiver, right, I have like two dots and I have arrows. How many arrows do I have? In this case, it's going to be the number of maps between F and G, where F and G are as above. And so the stable representation that K corresponds to has dimension vector M1, M2, where those are the powers that showed up in the valence and spectral sequence. So the reason to choose this crazy complex is because we know something about representations of Kronecker quivers, basically. And maybe the most salient point is that the association of my vector bundle to K, which is just this complex, I can think of as defining a map from the moduli space to the space of stable Kronecker modules, stable representations of this Kronecker quiver, and we call that the Kronecker fibration. So I have it's a rational fibration of my moduli space over the space of Kronecker modules, and we can exploit that structure is the main point. Okay, let me state the main theorem now. So the main theorem is going to be a little complicated, but bear with me. Here it comes. Here's the setup. I have two Chern characters of stable sheaves, or stable bundles, I guess, because I'm really talking about the rank at least 2 case. I'll say maybe something about rank 1 if there's time, but there probably won't be. Okay, and then here are the assumptions. I'm going to assume the moduli space is positive dimensional. That's essentially not an assumption at all. That's just saying it's not exceptional. That case is already covered. I'm going to retain this assumption that one of my characters be sufficiently divisible. And for the ease of exposition, I'm going to assume that the tensor product is non-negative. Of course, if it's negative, I can do Serre duality type things. So this theorem really is going to tell you in every case. So this is just a simplifying assumption. Okay. And then I'm going to take V and W with primary corresponding exceptional and complex K associated to V. So I'm going to take E plus and K dot associated to my vector bundle V, as I've defined for you now. So the theorem breaks into 3 cases. The first case is if the Euler characteristic of V tensor E plus is not positive. And you'll notice W doesn't show up here at all, but it turns out that doesn't matter. No matter what W is, as long as I have this Euler characteristic, then V tensor W has the expected cohomology. So I guess I didn't define for you the complex K in this case, but it turns out to not matter. Okay, so that's case 1. Okay, case 2. Okay, maybe the Euler characteristic is positive, and then I can ask about the rank of the associated complex K. And of course, it's a complex. It's concentrated in degree -1 and 0. So its rank can be less than 0, or equal to 0. And if that's the case, then V tensor W has the expected cohomology. Okay, so that was case 2. Case 3 is the more complicated one. Okay, so like case 2, I have the assumption that the Euler characteristic with the primary corresponding exceptional is positive. But now I'm going to assume the rank of K is positive. If that's the case, then I distinguish 2 subcases. And now for the first time, and only now, does the vector bundle W actually appear in the assumptions. So if I have the Euler characteristic of K tensor W is positive, or if its tensor product with the primary corresponding exceptional for V is negative, then once again, V tensor W has the expected cohomology. For the general V and W. So the final case, 3B, is the only case where we get unexpected cohomology. So I need to be in case 3 and not in case 3A. And then the cohomology groups are as follows. So H naught of V tensor W is the Euler characteristic V tensor E plus times the Euler characteristic W tensor E plus dual. I think I've got all my duals right. I think. And H1 of V tensor W is minus chi of K tensor W. Okay, so that's the theorem. The theorem says that outside of the very specific conditions of the tensor products having various Euler characteristics, I have the expected cohomology. And only in this somewhat rare, it turns out, case do I actually have the unexpected cohomology. And it's given precisely by this formula. So that's the statement of the main theorem. Any questions about that? Okay, so in a minute, I'm going to show you some pictures that will help you sort through this, because I realize that there's a lot of definitions and a lot of Euler characteristics, and it probably looks kind of arcane. But let me actually do first a very quick example of a very explicit computation. I hope you'll find this edifying at least. So I wrote down, have to find in my notes. Okay, so I'm gonna give you 2 Chern characters. I'm going to give you V to be the Chern character 2, 1, minus 5 halves. That's the Ch2. And W will be 4, 2, minus 6. Okay. So I can tell you the tensor product has Euler characteristic 0. And I can actually tell you a little more about these things. The general element of M of V has a resolution that looks like this. Goes to this. So this is for the general V in its moduli space. And the generic W has a resolution that looks like this. I don't know that we need to know this, but here it is. I think this is to the 8th power. Okay, now what are the associated objects that I defined above? So the primary corresponding exceptional to V is O. It's just the line bundle O. And what is the complex K? The complex K is this thing that you already see to the left here. It's this O of minus 2 squared goes to O of minus 1 cubed. So somehow this thing is telling me about K, and this thing is telling me about the primary corresponding exceptional. Okay, and then what am I supposed to do for the theorem? I'm supposed to compute like chi of V tensor this, right? V tensor, its primary corresponding exceptional. In this case, it's just the Euler characteristic of V, and I think that is 1, so that's positive. And then the other things, that means I'm in case, I'm in either case 2 or case 3. I can look at the rank of K, And I see that the rank of K is 1, right? 3 minus 2. So I know I'm in case 3, so I'm here. And then what do I have to look at? I have to look at chi of K tensor W, which is minus 1, and chi of E plus dual, which is just O, tensor W, which is 1. So that puts me in case 3b, I think. There's something in chat. Is K a sheaf in this case? Yeah, K is a sheaf in this case.
Mm-hmm.
That won't always be true, but it is in this example.
I think chi of v is 0, but I don't think it matters.
Chi v 0 could be.
It's chi of o minus 1, chi of o minus 2 are 0.
Chi of o minus 1. Oh, yeah, maybe that's right.
No, v has an O.
V.
Oh, there's an O.
I have an O right here. Yeah.
Okay.
Okay, good. So where are we? We've computed all of the numbers we need. And so the theorem now tells me that H naught of V tensor W is chi of V tensor E plus, which is 1, chi of W tensor E plus dual, which is 1. So I have 1 H naught. And then H1 of V tensor W. Well, we know it has to be because we know the Euler characteristic of the pair is 0. We know it has to be 1, but we can see that from the formula. It's minus chi of K tensor W. That's minus minus 1, so that's 1. Okay, so the theorem tells me how to compute that. And the spirit of what's going on here is that, roughly speaking, this complex K and this this primary corresponding exceptional somehow show up in the resolution of my sheaf. And it's their properties that matter for the computations. Okay, let's draw some pictures. So the pictures are going to be a little complicated because the classification of Chern characters of stable sheaves on P2 is a little complicated, but let me sketch it very briefly. So this is essentially due to Drézet and Lepotier. And by essentially, I mean literally, I guess. This is the Drézet and Lepotier classification of stable sheaves on P2. And so what I've drawn is actually R2 with coordinates mu and delta. And what Drézet and Lepotier say are there these sort of, oh man, I'm not drawing very well, these parabolas that intersect in this kind of fractal-like way, but they're defined based on exceptional bundles. And what they say is that if I'm above this funny curve, this funny curve defined this way, whatever that is, then I have stable sheaves of those Chern characters. And if I'm below the curve, so that's in the shaded region, if I'm below the curve, the only stable sheaves are the exceptional ones. And so there's some points here. Right? Here's the coordinates of the tangent bundle twisted by -1, I guess. Here's anything on the delta equals 0 line are going to be line bundles. And then there are more complicated things in between. And so, so this is the basic picture of the classification of stable sheaves. Dimitri talked a little bit about this in his talk about P1 times P1. Of course, in P1 times P1, there's more dimensions, so it's more complicated. And the picture that you should have in your head is I should take the parabola consisting of Chern characters that are orthogonal to V. So I have my character V, and it defines some parabola that looks like this. This is a parabola consisting of Chern characters that are orthogonal under the Euler pairing. The corresponding exceptional bundle is the one, it's the exceptional bundle that sort of lives underneath the place where the Drézet-Lepotier curve intersects the orthogonal parabola. So it intersects like here. And so that's in the zone controlled by the bundle O. And so I know that that's the corresponding exceptional. So the definition of corresponding exceptional is somehow supposed to capture this fairly clear geometric picture. So that's what that is. Let's do another picture. So case 1 of the theorem says V tensor, the corresponding exceptional is less than 0. So that's actually, I think I already drew that. So the orientation of this is V perp. is that if I'm, oh, I've drawn it wrong. I haven't drawn it right. This one looks like this. This is V perp. So the orientation of this picture, if you work through your Euler characteristics, is that everything above the orthogonal parabola is where the pairing with V is negative. So here my corresponding exceptional is O, and you can see it's above the parabola. So that's putting me in case one. And so what case one of the theorem says is that if this is what the picture looks like, then V tensor W will not have special cohomology. Okay.
Do you need the divisibility of W to prove this, to prove case one?
Yeah. So that's a great question. The only time that we don't need it is actually, well, I'll draw some pictures later, but in this case, we really do need it. Yeah, this case seems to be particularly hard from that perspective. Let's do, let me show you case two and case three, and then I'll say a little more about that. Okay, so case two is where the Euler characteristic is positive, and the rank of K is negative or non-positive. So this picture looks like this. Hello? Okay, here it is. So this is when my orthogonal parabola meets the Drézet-Lepotier curve on this left branch here. So the fact that the Euler characteristic is positive is saying that the corresponding exceptional has to be outside of the parabola. And the fact that rank K is negative corresponds precisely to the fact that I'm on the left side of the Drézet-Lepotier curve. And so again, you can see that this like fairly opaque condition of having negative rank corresponds to something actually reasonably intuitive and geometric. Although maybe it's not clear why that's important, you can at least see it on the picture and see what that means very clearly. So that case two, again, this has expected cohomology. Okay. And then case three was the complicated one where there was unexpected cohomology. So this is a picture that let me take a minute to describe again. This is one pulled straight out of the paper, and the coordinates are a little different from the above picture. So let me explain it again. Okay, so all this stuff here is the Drézet-Lepotier parabola. Now in this picture, already drawn for us is the orthogonal parabola to V perp. Wow, I did a really terrible job tracing that. You just pretend that I traced that line very accurately. And you can see here's the corresponding exceptional bundle, which is now denoted E plus. Last time I think it was O. Here's E plus, and you can see it's below the parabola. So that's the same thing as the Euler characteristic being positive. And then rank K is greater than 0, just means that the intersection point of my orthogonal parabola to V with the Drézet-Lepotier curve is on the right side, not the left side. Okay, so that's case three. Case 3A is when we have the following Euler characteristics. And if you trace through what these things are saying, they're saying, look at the orthogonal parabola to K, which I'm now doing in green. Apologies to the colorblind among us. So this green thing is K perp. What these inequalities are saying are that case 3A corresponds to being outside of this shaded region, and case 3B corresponds to being inside the shaded region. So this shaded region is 3B.
Maybe you want to say that the coordinates on this plane are the slope and discriminant of W.
Oh, yes. Yeah. So thank you, Jack. So right. So the slope and discriminant are my coordinates on the plane, and I'm sort of drawing all my parabolas and asking where are my Chern characters of W. So if W is in the shaded region, then that means I'm in case 3B. And if W is outside the shaded region, that means I'm in case 3A. Thank you. So 3B, if W is inside the shaded region, all this data constructed from V, that was when I had unexpected cohomology. So the picture that I'm trying to convince you of is that not only does V have to be somewhat special in order for there to be unexpected cohomology, but even if V is special in that way, meaning that the Euler characteristics are as follows and the rank of K is as follows, then W also has to be kind of special. It has to be in this funny triangle here. And you can also see in this picture, you can see the coordinates U plus. That's this intersection point where these three parabolas are all meeting. That's the U plus from the paper of Göttsche, Huizenga, and Wolf that I mentioned at the start of the talk. And what's remarkable about that point is that what our theorem is saying, it's getting a little messy. Let me erase some stuff. So I'm talking about this point here, the U plus. What our theorem is saying is that maybe up to scaling, if I proceed along the orthogonal parabola to V in this way, I have expected cohomology. However, if I proceed along it this way, I have unexpected cohomology. So U plus is extremal in some sense among Chern characters for which the cohomology is expected. And since it lies on the parabola orthogonal to V, it's saying that the general element of this moduli space has no cohomology when tensored with the general element of V. And so this maybe justifies this thing somehow telling me about the edge of the effective cone, so that this thing is extremal along this. Okay, and then maybe let me say a little bit about Aaron's question, which was, where do we actually need this assumption on the scaling of W? So let me try to draw a picture that I think is accurate, and if it's not, Izzet or Jack can correct me. So it's true that we don't actually need the scaling assumption on W everywhere that we use it. I think we need the scaling assumption on W maybe above this parabola that I've drawn. So this is the extension of the orthogonal parabola that's from the Drézet-Lepotier curve. And Drézet and Lepotier curve kind of stops, it has a peak. But if I just let that parabola on the left keep going, then I don't need to scale W if its Chern character is on this side of that parabola, I believe. So that includes the shaded region. We don't need the scaling for W. And since I have maybe 2 minutes, let me briefly explain where that scaling comes from. So the scaling is somehow in this region up here. And the reason is essentially that our techniques don't work, basically. What we do instead, the reason that the scaling shows up is we're doing things like elementary modifications. So I take like some Chern character of W here, and maybe I prove the theorem here, and then I do elementary modifications on that bundle to go up. But then that requires me to scale the rank. I don't have enough control over the rank of the elementary modifications. Along the orthogonal parabola, we have a similar problem, the orthogonal parabola to V. We're not actually proving it for a given Chern character here. We're proving it for the U plus and the U minus, which is over here. And then we're constructing exact sequences that produce things with Chern characters on this side of the orthogonal parabola, but they don't necessarily have the rank we want. So somehow the techniques fail a lot in this upper part of the picture, whereas in the lower part, they work. Anyway, let me stop there. Thank you all.
Thank John. Very nice talk. Are there questions? Well, I have an awful question, which is there anything that can be done for P3?
I mean, P3 is bad, right? Like,
yeah,
I need, yeah, I need irreducible moduli spaces and things like that for me to frame this question very well.
Good found in P3.
Yeah, we use a lot of things that we know about P2. We know the classification of stable Chern characters. We have, we know all the exceptional objects. I guess maybe we know a lot of exceptional things on P3 as well. Yeah, I personally don't think I can do P3, but it would be interesting if someone did.
I mean, the point of this, these E, F, and G are sort of to find a really good presentation of the general bundle, right? The
Yes.
given character.
So
So
you do have, you still have a balance in spectral sequence. You have exceptional collections. So you do get that kind of thing. I think there's a lot more to worry about too. Like you have 4 cohomology groups. So all of a sudden, if the Euler characteristic is negative, you have to worry about whether it's H1 or H3, things like that.
Also, the E, F, and G on P2, they're really chosen so that this corresponds to the birational geometry of the moduli space. Right, they're chosen so that kind of this exceptional twist, which starts from E plus and gives this 2-term complex F and G, that is the final model in the minimal model program. So I think maybe more interesting, or I mean certainly P3 is interesting, but it seems really hard. A similar question is, can you do this kind of thing for other surfaces by using the same kind of setup?
I think other surfaces would be more tractable than P3.
well, and you have some results on Hirzebruch surfaces now too. So, or some of you.
Yeah, I mean, any surface where you already know what the cohomology of a general bundle is a candidate for this kind of thing, right? And that's a short list. That's Hirzebruch surfaces, some K3s. You can ask Izzet which K3s, things like that.
Anybody else want to ask anything? Okay.
Or maybe can I remark something? Not really a question, but since you asked about P3, I think, I mean, of course, this is not very realistic probably to do this in this kind of generality. But if you want to deal with this problem to figure out that some cohomology groups vanish, right, so that the other characteristic tells you everything, you might be still able to get an H2 vanishing if you look at frictions like a tilt stability. And you can sort of you can use said duality and you maybe can get a vanishing from stability. But I mean, that's certainly not enough to do something of this magnitude.
I mean, maybe the other question you can ask that might be more tractable is whether you can find a pair of sheaves with given Chern characters that have the expected cohomology. Like you might be able to certainly in certain ranges in any PN you can construct some of these things. The question is in greater generality on the assumptions of the Chern character, whether you can construct it. Like rather than asking for, if you're given 2 stable sheaves, general stable sheaves, like if you want to find an example, that might be more tractable.
Nice. Okay. Well, if there are no further questions, let's thank the speaker. And I guess this is a